All right, so we're going to talk today about the ellipse. And as you can see from this demonstration, an ellipse can be made by having 2 points that rotate around using an equidistant from those points at all times. Now, the nice thing about this is that we can see that it's really focused on 2 points. Okay, and we're going to learn later that we're going to talk about how those are the focal points for the ellipse itself. But this simple demonstration using a rubber band and 2 thumbtacks gives us a pretty good idea. An ellipse is a set of points on a plane, the sum of whose distance from 2 fixed points is constant. Each fixed point is called a focus, or foci for plural. So as we see, going back to that animation, we see that we have the 2 foci are going to be those 2 blue thumbtacks. And we see the pencil being equidistant as a summation. In other words, the distance from here to any given point from here to here, if this is x and this is y, x plus y is a constant. Okay? So even if I allow the animation to continue and this was to rotate over here and we had a new point, I would say this is my y, this is my x, but x plus y is still that same constant. So, the major axis is the longer axis. And it can be either horizontal or vertical. We can either have a long distance here, or we can have the longer distance here, but the major axis is the longest distance. The minor axis, going to be shown in red here, is the shorter distance, or the shorter thickness, if you will, just to make it a little bit easier. Now, as we get something like this, as we get on the left-hand side, this object here, as we get closer and closer to being a circle, it becomes more and more difficult to discern whether or not we have the major or minor axis. And as we get infinitesimally close to the circle, we wind up getting where the major and minor axes are almost becoming equal. So the ellipse with the center at the origin. Okay, that means we're centered at 0, 0. That coordinate point. Okay. The horizontal major axis, and the equation is this: x squared over a squared, y squared over b squared, equaling 1, where a is greater than b and b is greater than 0. So we're not talking about any negative numbers down here. Okay, we're not dealing with any negatives in the bottom half of our equation. It does have vertices at plus or minus a, and the endpoints of the minor axis, okay, is at 0, plus or minus b, and the foci plus or minus c, where c is equal to c squared equals a squared minus b squared. And c, of course, again, is greater than 0. We're not talking about any inverted or imploded diagrams. Okay? So let's take a look at what we're talking about here. If I have that equation, here's my primary equation. Okay? There's my primary equation. Here's what I can find out about it. Now remember we said A is greater than B. So again, we're talking about an ellipse that has its major axis in the horizontal position. We said that A is greater than B, and B, of course, is greater than 0. So I can see that this A squared on the bottom, what it does is elongate, okay, my circle. And we can see that if I take A, I take minus A and plus A, those are my x values. Again, assuming that this is origined or centered around the origin. I can also see that my B, that this B squared, if I pull that B value out, my B becomes my plus and minus Y values for my ellipse at the vertices. So here are my plus or minus and my vertices. Then I have my foci. And my foci are here highlighted in blue. And there's that C value, that plus or minus C value that we talked about. And again, we said, just to reiterate, okay, that C squared is equal to A squared minus B squared. So we have C squared is equal to A squared minus B squared. Okay? So there's our ellipse horizontally and how we can obtain those values. The ellipse with the center of the origin in the vertical major axis, and the equation x squared over b squared plus y squared over a squared. Because the reason we swapped these two is because we want this to be true. We still want a to be the greater value and b to be less than that, and of course both of them larger than 0. It does still have vertices at 0, plus or minus a, because we swapped these. It doesn't mean that the vertices changed. It just means they're going to change their elongation. Okay, and we have plus or minus b for another one. And the foci again at 0, plus or minus c. Notice that c now is in the y position, because we've changed the foci 90 degrees. However, we still, because we swapped these two, we still have c squared equals a squared minus b squared. Still the larger value squared minus the smaller value squared. We are not going to deal with anything where we get c squared is going to be less than 0. Because if we did, then we'd be talking about c squared is equal to, let's say, negative 2, which means c is equal to the square root of negative 2, which means c is equal to I root 2, and we are not dealing in the imaginary world. No Winnie the Pooh action here. We don't want that. No Piglet. Okay? No Tigger. None of those guys are going to be involved. So here again is our graph analyzing this in the vertical position. Our equation, much the same, except for we swapped A and B. Because now A, again, A is greater than B is greater than C. I'm sorry, greater than 0. We can't really say it's greater than C. Okay. A, being the larger value, is attached to the y, which is why in the y direction, we have the larger axis, or the major axis. Again, we see here that we take this A value, and it shows up in the larger axis. We take our B value, and it shows up itself in the minor axis. Our foci look very similar, except for instead of the C being in the X position, the C, the plus or minus C, are in the Y position, because now our foci are elongated along the Y axis, or in a vertical position. They're no longer horizontal. So here is a problem that we have. Sketch a graph of the ellipse. Label the vertices, foci, and endpoints of the minor axes. So here is how we would start. If this is our primary equation, we know, going back, that we're looking for something equal to 1. So we know we need 1 on the right-hand side. We need this 1 here. So to get that 1, we're going to divide both sides by 400. Because that will give me 1 on the right-hand side. Now, it makes me do a little work on the left-hand side. But we can handle that. I divide both sides by 400. I get 400, 400. I do a little quick breakdown of this. This winds up being 1/16. I get x squared over 16 plus y squared over 25 equals 1. Again, we notice, much like a Fisher-Price problem, the numbers are working out nice and neat for us. But that's okay to start with. We can see here that our larger value, which we know is going to be our a value, a, again, greater than b, greater than 0, we know that our axis, our larger axis, is on the y section. So, here is our problem. We know that we have this on the major axis. We know that we can take the square root of 25 equals 5, or plus or minus 5, if you will. So we know we're going to get 5, negative 5. Here we have 16. We take the square root of 16. We get plus or minus 4. We know we get minus 4 here and plus 4 here. I now have my 4 vertices graphed. I then have to find C. Again, for us, some pretty simple mathematics at this point in our careers. We take 25, we minus 16, we get 9. We take the square root of both sides, we get 3. So our foci is at 0, plus or minus 3. So here's our 0, plus 3. Here's our 0, minus 3. I can now graph very simply by taking this point, connecting it to this point, connecting it to this point, using the best soft curve I can. And there is our ellipse. This will end part 1. Part 2 will begin dealing with dealing with another one of our ellipses.